Alright, so let's try to solve the next problem, which is 583 of your white textbook. The statement of the problem is a 1/40th scale model of a ship's propeller is tested in a tow tank at 1200 revolutions per minute and exhibits a power output of 1.4 feet pound force per second according to Faraday scaling laws. What should the revolutions per minute and horsepower output of the prototype propeller be under dynamically similar conditions. Solution of this problem: using Faraday's number, Fr is equals to ratio of inertia to gravity, so which is u square upon gl, and also using example 5.3 of your textbook as a reference to solve the problem. So let's say the prototype of propeller is P is a function of Q, the flow rate, D, the diameter, omega, rho, and mu. We have a set of repeating variables, so those are rho, omega, D are repeating variables. Alpha, the scaling laws are about 1:40 of scale. So omega of prototype to omega of model ratio would be equals to time of model to time of propeller, which is equals to square root of alpha. Since omega is equals to 1 by T. Omega is revolutions per minute actually. So this implies omega of prototype by model revolutions per minute are 1200 rpm, which is equals to square root of alpha, which implies omega of P would be equals to 1200 rpm multiplied by 1 by root 40, which implies thus omega P is equals to 1200 by root 40, which is approximately 190 rotations per minute. To find the output power, so the power of prototype to power of model would be equals to the repeating variables, which are density of the liquid for prototype by density of model whole times. I'm directly jumping over here. I have not solved the step-by-step method to get over here, but so I'm taking example 5.3 as a reference. From there, omega P by omega M whole raised to 3 multiplied by dP over dm. So this is the same steps that we did it in the previous problem 577. So we tried to calculate the powers of rho uh, v l. In that case, here we equate power, the dimensions of power, and to the dimensions of these repeating variables, which are rho, omega, and d. And that's how the power of omega and d have come out to be 3 and 5, and the density as 1. And then we substitute back them into the equation, and after rearranging, we do the math, which would be which would implies, so p of p would be equals to pm times rho p by rho m multiplied by omega p over omega m whole cube times dp over dm whole raised to the power of 5. So from the values that are given in the problem statement, we can clearly substitute seconds. So power of prototype would be equals to, the output power of the model was given as 1.4 feet pound force per second. So we substitute that in place of pm as 1.4 multiplied by the revolutions per minute, sorry, the density. So density for prototype and model will be the same fluid that is passing both in model and fluid will be the same. The density of prototype and fluid would remain the same, because in both cases the density of the liquid will be the same. So rho p would be equals to rho m is equals to rho, and rho gets cancelled to get as value of 1 multiplied by as we have seen in the previous step, omega p over omega m is a ratio of 1 over root alpha, so that is 1 over root 40 and whole raised to the power of 3. Multiplied by dp over dm. The ratio of them is 40 whole raised to the power of 5. From this, when we calculate, we get p power of output power be about in terms of horsepower. Before that, we get an answer of 567,000 plus 550, and we convert it to horsepower, giving us, implies, would be equals to 1030 horsepower. And that's the end of solution for this problem. If you do have questions, you're free to ask me. You can contact me on my email, or I'll be available on Microsoft Teams, and I'll be available for you to answer any questions that you have. With this problem, we end our this week's discussion session. I'll be seeing you next week with new set of problems. Thank you.